Swayam Prabha. Digital India. Educated India.
Hello, welcome back. Today we will discuss the reactivity of these carbene complexes that we were discussing in the last class. We have synthesized the carbene complex in the last class. We have seen examples of each of Fischer carbene and Strock carbene. In today's class, we will discuss the effect of these carbene complexes in organic synthesis. Simply, these carbene complexes has revolutionized the organic synthesis in a way, so that now carbon-carbon bond formation is possible in a very controlled fashion. Any new carbon-carbon bond, if one would like to synthesize, he or she can take the advantage of the metal carbene species. We will today see first the olefin, two of them are reacting to give a newer olefin. The next we will discuss olefin and carbonyl complexes reacting to give a newer olefin. So, both these processes we are getting a new olefinic compound. So, if one is interested in synthesizing any new carbon-carbon bond containing compound, he or she can think about having a double bond at the beginning, and then if they want to reduce it or further oxidize it depending on the demand, one can plan accordingly. But by these carbene complexes, one can think of generating a olefin, or so to speak carbon-carbon double bond containing compound, and from there on further characterization or further transformation can take place. First, let us look at the one example that we were discussing in the last class, where one of the olefin is reacting with another olefin with the help of metal carbene complex to give you a newer olefin. Let us look at that example. In this particular case, the starting material are having a double bond or the olefinic in nature, which are 150 kcal per mole. Now, this reaction can be done at room temperature. So, this metathesis reaction, it is done at room temperature. One of the partner is exchanging with another partner to give you a newer compound with olefin. Metal is used as a catalyst, and often it is used as under thermal reaction condition. Also, these reactions are reversible in nature, and therefore, we can have a quite good number of synthesis of this compound without much problem. This is once again catalytic is in nature, and metal carbene is used as catalyst. These are done under the thermal condition. Concentration of the reaction can be varied during these processes. Now, we will look at carbonyl olefination, where one of the carbonyl complex will be involved during the synthesis of this final compound. So, let us say for example, we are starting with a metal carbonyl complex, okay, metal carbonyl RCOX and a metal carbene such as this one. If you exchange the partner at this point, what you can get is a new olefin complex with the R prime which was associated with the metal center now exchange to give you the metal oxo, which is a very stable complex. This is usually very stable complex, and a new carbene or a new olefin is generated. These reactions are usually irreversible in nature, and therefore, one would think that this metal olefination, where it is going with the help of carbonyl species, are going to be not only irreversible, metal carbene need to be used in stoichiometric version. The first example which we were discussing, where two different carbenes or two different olefin was reacting to give you a newer olefin, those reactions are usually reversible and metal is used in catalytic quantity. The latest example, where carbonyl is used with another metal carbene to give you a newer olefin, in this case metal catalyst is usually used in stoichiometric amount, because the reactions are irreversible in nature. The previous reaction was reversible in nature. Since this is irreversible, the latest one is irreversible, we need to use stoichiometric variation or stoichiometric quantity of the metal carbene. Nonetheless, this gives the access to the olefin from carbonyl compounds, which is quite amazing if you are thinking about the potential of these reactions for organic synthesis purpose. Now, we will look at some more example of these olefin complexes, where you have one olefin is reacting with another one. It could be intramolecular, it could be intermolecular, depending on the demand of the ring size. We can have a dilute compound or dilute reaction condition or a concentrated reaction condition. In any way, we will first discuss the 2+2 and retro 2+2 with one of the examples, so that the mechanism of these reactions become familiar with you guys. Let us look at one of the example of olefin metathesis. Okay. So, we will discuss olefin metathesis. Most important application of this type is ring closing metathesis of diene. So, ring closing metathesis of diene, which is most popular, and you have, let us say for example, one starting material which looks like that. You can have any variation over there, and you can take catalytic amount of metal, which will go, the reaction will go in the forward sense and give you this compound, and you will have ethylene coming out from this reaction. Overall, if you look at, the reaction will start in a reversible fashion, where one of these terminal olefin will react with the metal carbene to give you, it is a 2+2 between this olefin and this metal carbene to give you the metal is in metallocyclic form and 4-membered metallocyclic form to with the olefin hanging right close to it, or this ring size can be very big, that is of no problem. Usually then by retro 2+2, you will have the metal inserted with the organic complex. So, a newer organometallic intermediate, so to speak, in this case newer metal carbene is generated. Once metal is incorporated within the organic molecule, then you can have a 2+2 once again to give rise to the metal containing new compound, which is now ready to give you or leave the metal in a metal carbene form. If this metal carbene comes out, and then you can get the desired product. So, as you can see in this example, starting with 2 terminal olefin, we have a metal carbene intermediate reacting with one of the terminal carbene to give you the 4-membered ring. From there on, we can have then a 2+2 to start with, and then a retro 2+2 lifts the metal into the organic substrate, which then can further undergo reaction with another olefin in a 2+2 fashion to give you the cyclic complex, from which you can have a retro 2+2 to leave out the metal carbene. So, therefore, you can see this reaction can be catalytic in nature. Overall, it stitches the two terminal carbene to give you an internal olefin. So, two terminal olefin can give you finally a stitched version or a cyclic version of the organic compound, where the double bond is placed in between of those two terminal olefinic center. This is an extremely powerful technique to generate small size or even huge size or large cyclic compound by utilizing the beneficial features of the metal carbonyl metal carbene species. Now, this metal carbene species is used usually in these cases in catalytic amount. You can recover this metal carbene complex from this reaction, but most importantly the desired carbon-carbon bond can be generated. So, if you have a large molecule, let us say you are planning for a natural product synthesis, you can split your large molecule into half. It could be exactly at the middle or even a little bit on the side. Now, as long as you split it there, you individually synthesize these two fragments, and in the final stage during your end game, you want to utilize those two fragments with terminal olefin with the help of yet another metal carbene to put them together, and then subsequently you can do oxidation or reduction of that newly formed double bond to give you to get the desired compound. So, this olefin metathesis reaction has heavily been utilized both in industry as in academia, most importantly in bigger molecule synthesis, much more complicated molecule synthesis which were previously unthinkable. Now, that is delivered in a really scientific manner and in real controlled fashion. Okay. Now, we will try to take a look at the little bit other examples that we will be able to generate from these reactions. So, what happen, you can have a bigger ring size reaction. When you have a bigger ring size, then the reaction is controlled under the dilute condition. Okay. If you want to really go for a bigger ring, you have to make it dilute, so that your competition experiment intermolecular competition can be ruled out. And if you are having a smaller ring, of course, it is both entropically favored as well as kinetically favored, and therefore, you do not need to do the reaction under the dilute condition. If it is a bigger ring, one usually need to synthesize this complex under the dilute condition. If it is a smaller ring, you can do it under any condition you would like to do. So, finally, therefore, by utilizing these techniques, you can have compounds such as where the olefin, where you have a alternate center and these could be polymerized, or you can start with an olefin where you have these two terminal olefin attached with it. You add the catalytic version of M double bond to give you the metal olefin compound, from where on you have this cyclopropene, cyclobutene intermediate, and finally, this can lead to the polymerization of the intermediate, which can go for ring opening metathesis polymerization reaction. So, these are called ROMP or ring opening metathesis polymerization. Now, these are also very powerful technique one can think of and can utilize this technique to generate very complex molecule. Now, we will discuss one of the example which Grubbs has first done it and utilize actually Strock carbene. As I was discussing, the Strock carbene was discovered in 1974, and Grubbs really came up with the Grubbs catalyst in 1993. In between, of course, Grubbs was also working on this area, organometallic area, but that time he was using Strock carbene to do these transformations. Let us look at one such example where Strock carbene was used by Grubbs to do these metathesis reactions. So, Grubbs, again this before 1993, Grubbs was using Strock carbene. This is in 1992. We are going to see 5 to 7 member ring formation, 5 to 7 member ring formation example, where the starting material is the one with 2 terminal olefin, and you have very beautifully substituted compound. Now, one would be able to see that we should be able to generate these 2 compound outside, and to give you the stitched compound or the ring compound. If when Grubbs was using Strock molybdenum complex, of course, you can have tungsten complex, nowadays that is also used. 5% of this Strock molybdenum complex is giving you the ring closure between this carbon center and that carbon center to give you a 5 membered intermediate where olefin is in the middle, and the substituted this compound can be synthesized in 93% yield. Okay. By using this technique, of course, one of the problem which is encountered by this Strock carbenes is they are not that not that tolerant towards various functional groups, such as acid, alcohol, aldehyde cannot be tolerated by Strock carbene method, or while utilizing Strock carbene we see acid, alcohol like CH2OH or aldehyde can usually not be tolerated under the reaction condition. This is where actually Grubbs catalyst become very popular and of course, perhaps widely used, because the functional group tolerance is much more in Grubbs catalyst compared to the Strock catalyst. That is the reason why perhaps Grubbs catalyst is used and sold worldwide in a large quantity, and also in industry it is used quite hugely. We will now see one example where different functional group can be tolerated by using Grubbs catalyst. So, Grubbs did this reaction in 1993 to start with, where these terminal olefin, 2 of them are stitched together in presence of various X. This X could be your CO2H, X could be your alcohol, X could be your aldehyde, and so on. Overall, it gives you the complex what we want, cyclohexene complex with X substituent or these functional group substituent. The yield was quite good and it was tolerated. Most importantly, it was tolerated, yield was also quite good, 82% for the aldehyde complex. So, overall what you have seen then, Grubbs ruthenium catalyst or these carbene complexes are more versatile, can tolerate wide variety of functional group compared to the Strock carbene complexes, and this is where Grubbs catalyst has some sort of advantage, and we see both in the literature and industry it used quite extensively. But the groundwork, the most important discoveries were actually done at the beginning by Strock group. So, it is a very useful method. It is both nowadays both Strock carbene as well as the Grubbs catalyst are used for this purpose, but cases where we have sensitive functional group, usually Grubbs catalyst is preferred. It is usually seen as more versatile and quite widely used. Now, let us look at some more of the example while we discuss the beneficial features of this beautiful technique. Now, first we will discuss an asymmetric version of this reaction. Asymmetric version is mainly discovered or explored by mainly by Strock and later on joined by Hoveda. Strock-Hoveda catalyst or Strock-Hoveda research group, both of these research group put together a beautiful version of the asymmetric catalysis, and these are the one which are most interesting in the current literature context, and it is quite widely studied at this point. Okay. Let us look at one of the asymmetric version of the of these carbene reactions where the metathesis reactions are going on. Let us look at that. Asymmetric ring closing metathesis. This is done by Strock with Hoveda. Okay. Now, the starting complex, of course, you have to have a monosubstituted olefin, or they have had a monosubstituted olefin, which is the most reactive one compared to the disubstituted or internal one, and you have this species where you have two enantiotropic phases of these olefin. These two phases are enantiotropic in nature, as you can imagine. Now, these one of these centers we can react with the other one to give you the cyclic silyl complex, and the final complex, as you might will be able to predict at this point, would be the one where you have this complex formation and you can get this in an asymmetric ring closing metathesis version. The thing that is used for these cases are the one where you have the enantiomer of one of these substituent is used, and overall you can get a very good EE for this product. The molybdenum catalyst is used, as we were drawing in the previous class. You will have these complete tertiary centers, and this is your binol catalyst with aryl group in there. This is the one which is synthesized and utilized quite beautifully, and we have very high EE for this reaction. This is done by Strock with collaboration with the Hoveda group. Now, that is quite interesting. As you see, we have a beautiful reactions going on, and you can get the asymmetric version of it, starting from a material where you have a terminal olefin with the silyl, and the one where you have two enantiotropic phases or enantiotropic phases. Now, we can get these complexes quite in an enantiomeric form. Okay. That is very interesting, and it can be done in a very asymmetric, very high EE. Now, we will react or give one example where Grubbs catalyst is utilized, and we can synthesize the beautiful compound starting from 2 olefin and 1 alkyne in the middle. Let us look at one example where olefin and alkynes are together. What would be the reactivity pattern and what could be the end product that could be determining a lot of reaction that one would like to plan in a retrosynthetic manner. Let us rank closing metathesis RCM of dienines. This is done by Grubbs again. Okay. Here what we will take is a compound, a little bit interesting one and exhaustive. It is synthesized in 28 steps from Aldrich available material. Well, quite elaborate synthesis, but finally, if you have this compound, what you can expect from this one, if you use 3% for example Grubbs ruthenium catalyst, the end product that you are going to get is quite interesting. You may want to try to draw it by yourself. What can you predict what could be the end product? As you can see, it is a 6-membered and 5-membered fused compound that we get. Now, look at the beauty of this synthesis. You are starting with 2 terminal olefins. In between there is an alkyne. Now, you are able to stitch the olefin with alkyne, and then resultant olefin you can further stitch with the remaining olefin. So, overall you have a olefin which is of course the one which is more reactive. It reacts first to give the metal carbene at the olefinic carbon site, and from there on it reacts with the nearby alkyne, because the olefin is really further away or the ring size will be bigger. So, therefore, it is not reacting with another olefin. The metal carbene is reacting with the alkyne to give the ring closure. From there on, the resultant compound now ready to stitch with the remaining terminal olefin to give you the beautiful fused complex with a 6-membered and a 5-membered ring. That is the beauty, that is the strength of such technique, where you can get this compound, get the beautiful compounds from a readily available or pre-prepared complexes. Let us look at the mechanism of these reactions. So, you have 2+2 reaction first. I will just put it very briefly. The left hand side I am keeping intact, only the right hand side I am trying to react. Of course, the olefin will react first. Here you are having 2 olefinic terminal olefin. One of them I am taking the right one, you can take also left one. Right one we have reacted by 2+2 and retro 2+2. We were now able to put the ruthenium within the organic molecule. Of course, OSI 83 is there. Now, once that is incorporated, this one can react now with the carbene, sorry, this alkyne, but this one will not go and react with this one, because this will gives rise to a huge member, I mean it is a larger ring size, right. So, this one will react with this alkyne to give first the 5-membered ring, and subsequently you can get the 6-membered ring. Let me draw the other intermediate. So, you will get that one first, and overall then this 2+2 would lead to the intermediate of 5-membered ring. From there on you can go ahead and let me draw the compound further. We can have overall a compound which looks like a 5-membered ring formation first, and ruthenium over there and methyl over there. From here on you have OSI 83. This ruthenium alkylidine complex now will react with this olefin to give you the final product. This is the product formation stage. So, overall what you have seen here, you have 3 reactive centers, 2 terminal olefin and 1 internal alkyne. Of course, as we said, the terminal olefin, any one of them will react first. This terminal olefin will undergo 2+2 and retro 2+2 to give the metal carbene into the organic molecule. So, you started with metal carbene, or let us say Strock carbene type of molecule. In this case we are using Grubbs catalyst. Now, Grubbs catalyst you use catalytic amount where you have a metal carbene species. Now, that metal carbene will react with one of the terminal olefin to undergo 2+2 and retro 2+2 and end up giving the metal inserted into the organic compound. From there on, it has 2 choices. It can react with alkyne and it can react with yet another olefin. Of course, reacting with the other olefin is more beneficial. However, that will gives rise to a larger ring formation, and therefore, the 5-membered ring formation preferred to react or to incorporate and engage the alkyne with the metal carbene. So, the 5-membered ring is formed first. Subsequently, the metal or ruthenium carbene species that we get that incorporate into the organic molecule, and then further it flips to the other side to give again the 2+2 and retro 2+2 to give you the final 6-membered ring. So, 5-membered rings forms first, and then 6-membered ring comes to give you this fused compound from a 2-terminal olefin and an internal alkyne. That is actually extremely exciting product formation. So, therefore, if depending on your final product, you can plan your end game and can do the remaining synthesis, keeping in mind that metathesis reaction is a useful technique and a very versatile and very reliable technique, and therefore, the planning of a synthesis can be relied on breaking or making of this carbon-carbon bond. So, in the next class we will be continuing from here on. We will see some more example of these complexes and reactivity pattern we will discuss, and till then you might want to practice these 2+2 and retro 2+2 to get the great feeling of these complexes. Keep practicing. We will come back soon with more examples and more discussions. Thank you very much.